All right, we're talking average rates of change. And we want to get talking about instantaneous rates of change. So we're going to use the equations this time. So we've got S of t equals negative 4.9 t squared plus 90. So we're just describing this situation where somebody lives on the 3rd floor in an apartment building and their flower pot is falling 90 meters to the ground. So t is time in seconds and S of t is distance in meters. So let's say we want to get the average rate of change. So we want to figure out the average rate of change between 1 and 3 seconds for this falling flower pot. We want to know the average rate of change between 1 and 3 seconds. So let's just say we were going to graph this so we can have a visual. Say it's looking like that. This is time and distance. And I guess that will be 90. And at 1, I don't really know where it lands on the ground, so this is very inaccurate, but we want to know the average rate of change between 1 and 3 seconds. So we're finding the slope of the secant. So we're just going to use our regular old rate of change formula. And we're going to calculate S of 3 minus S of 1 divided by 3 minus 1. So we're going to calculate basically y2 minus y1 over x2 minus x1. All right, so we need to find S of 3. So S of 3 is when you're substituting 3 in for time. So negative 4.9 times 3 squared plus 90 minus, then we're subbing 1 in, negative 4.9 times 1 squared plus 90. And we're dividing the whole thing by 3 minus 1, which is 2. Okay, so let's just see what we got there. Try that out. I'm going to use a calculator. All right, I got negative 39.2, and I still need to divide that by 2. Negative 19.6, and I guess my units will be meters per second. So that's my rate of change between 1 and 3 seconds. That's how quickly the flower pot is falling between 1 and 3 seconds. Now let's say I want a more accurate measurement right at 1 second, let's say. So that's not a horrible estimate, but I mean the slope of our tangent at 1 would be more like this. So when you look at this, compare the slopes of the blue and the purple line, they are different. So what would make our estimate better would be picking a point on the curve that's closer to 1. So why don't we do that? So let's work on trying to approximate the instantaneous rate of change at 1 second. Instantaneous rate of change at 1 second. So we're going to do it just the way that we know how right now. And then we'll develop some better tools as we learn more. So I'm going to back up. I'm just going to use another color. So I'm going to back it up and I'm going to find the rate of change between 1 and 2 seconds this time. So that way my secant's a little closer to the purple line's slope. So I'm going to go through this again and I'm going to, you know what? I'm going to make a little table to make this a little easier. So I'm going to have, so I know I need to find the change in y, I need to find the change in x, and then I need to find the change in y over the change in x. So I'm going to set myself up a little table. So let's say I wanted to look at the rate of change between 1 and 2 seconds. So the change in x, so let's say I'm doing S. So I'm doing S of 2 minus S of 1 And here I'm doing 2 minus 1. And s of 2 minus s of 1. So you just need to calculate that, like just like we did up here. S of 3 minus s of 1. So we're going through all of that, but we're subbing in 2 and 1 into those points. Okay, so I'm just going to do that. So I got negative 14.7. This is over 1. So I've got negative 14.7 over 1, which is just negative 14.7 meters per second. Okay, like what if I can get my interval a little closer? So why don't I pick an interval like between 1 and... So instead of 1 and 2, why don't I pick up 1 and 1.5? Let's get even closer. So let's figure out s of 1.5 and s of 1. And then over here I'll have 1.5 minus 1. Okay, so let me do that. So now I got negative 6.125, and then this would just be 0.5. So for my rate of change, I get negative 6.125 over 0.5, and I get negative 12.25 meters per second. Okay, not bad, but I feel like, why don't I back that point up a little closer? Why don't I try why don't I find the interval between 1 and 1.1? Okay, I'm gonna speed this video up. Pause at any time if you don't know what's going on, but I'm doing the same thing over and over again. So that is getting pretty close. So see my numbers? They're all approaching a value. I'm trying to figure out what that value is. So another idea I can do, because I'm really trying to figure out what the slope of this tangent line is. I'm really trying to figure that out. So I'm using closer and closer values. I could even use values on this side of 1. So why don't I try like 0.09, because that's really close to 1. So why don't I try those 2 points? So let me figure out the slope between 0.09. No, wait, what did I say I was gonna do? 0.09? No, what? Why don't I try 0.9? 0.9, let's do that. So we're just looking for values that are getting close to 1. I just thought I'd go on the other side of it. So I'm doing the same chart, but I'm just on the other side. So I'm going to try between 0.9 and 1. What's that look like? So I'll do s of 1 minus s of 0.9. And I have 1 minus 0.9. So that gives me negative 0.931. Then I'm dividing it by 0.1. So rise over run, so 0.931 divided by 0.1 will equal negative 9.31 meters per second. Okay, that's looking pretty close. Why don't I get even closer? Actually, why don't I just try to move that down? So I'm going to try to approach 1 from the top of it and from the underneath. So why don't I try like 0.999 and 1? So now I'm going to find I'm going to do s of 1 minus s of 0.999. And I'm going to do 1 minus 0.999. And I'm just going to do this all in one step. I got negative 9.795 meters per second. So what this looks like, in case it's not clear what I'm doing with like my 100,000 calculations, is I'm looking at my graph, and just to make it a little more obvious, say that's like 1, 2, it's kind of a rough thing. Okay, so I'm trying to find the slope of my tangent here. I'm just gonna zoom in. So what I'm doing is, in the red values, I was picking values that were like getting closer and closer and closer to try to approximate the slope of the tangent line. And then with my green colors, I was picking values on this side that are getting closer and closer and trying to find the slope of those, just to see if I could figure out what the slopes are approaching. And from the looks of things, as we go from, you know, like here we're getting closer to 1 and here we're getting closer to 1. So it looks like they're kind of converging at like around negative 9.8. Doesn't it look like that? Like negative 9.795. We'd round that up to negative 9.8. So I would say I would approximate the instantaneous rate of change at 1 second to be equal to negative 9.8 meters per second. And I did that by just using smaller and smaller and smaller and smaller value points, right? So in this average rate of change example, I used 3 and 1. So they were really far apart from each other. And I just kept picking points that were closer and closer and closer together, just to demonstrate. So that's how you could approximate the instantaneous rate of change